computer related thing in near future, in nowadays, they push out all new technology, and they have like a society, they have library that you can refer to. There are a lot of resources, so it's really good chance. And again, as school pays for you, you will simply get into the link and sign up for it. And I will drop the link in a minute.
Cool.
Thank you.
Okay. Looks like you're able to record it, Peter.
Yep, I got it. Thanks.
Yeah, I made you co-host. Sounds like that's what we needed to do. Okay, great. All right. So last class we spoke about Cisco's packet tracer, um, basically just a network simulation tool. A lot of things can be done there, and we're going to go and have a lab specifically about that in about a month or so. But you have the ability to go in and do an initial training if you so desire. It's free. And so before we have a lab on Packet Tracer, which is about a month out, we can, you can go through and get familiar with Packet Tracer before the fact. Let me share my screen and all right. Let me show you. So here is the course, Introduction to Packet Tracer 121 in English. And so this Introduction to Packet Tracer walks through how it works, introduction, using the user interface, simulation view, and they've got Packet Tracer basics, quiz, and so there's several chapters that will walk you through on elements of Packet Tracer and setting it up, putting the objects in there, connecting them together, and so forth. And there's other trainings as well on this Cisco Networking Academy. Since you've all signed up to get Packet Tracer and install it on your laptop, then you have access to these training resources under their Networking Academy as well, and can use those. So I might suggest that as a way to get up to speed on Packet Tracer. Okay, if we go to our class syllabus today, what we've got is today we're going to be going over data center design. And we'll go down to week 2 here. We've got data center design, power, cooling, enterprise networking, security topologies. And Peter, you want to talk about Thursday a little bit? You were thinking about maybe a virtual tour?
Yeah, I've got Zoom on my phone, so I figured I'd fire it up and take you on a little virtual tour of our data closet that we have here. We've got a couple server racks plus the networking for pretty much the whole campus. So yeah, that'll be fun.
Okay, cool. All right. So let's jump into this. And I wanted to talk about the basics. If we do a search for there's a term called hot aisle isolation. There's also cold aisle isolation. Okay. And you can do a search there and just go into images. And there's lots of images for this. Here's a good one that you can look up. Okay. And let's see if that makes it bigger. Okay. So as you're looking at this, in a data center, where you have a climate controlled, humidity controlled, power normalized cooling is all provided so that your servers can run optimally. In a data center, they have specific designs that are used throughout the industry. In this case, you see a picture here where you have, if I go down to this screen and zoom this up a little bit, bring it back up, see what it does here. Can I do that? Let me try it again. Okay, a little bit bigger. Okay. You have, at the bottom, you have a raised floor. A raised floor basically is a frame that's built that lifts the floor up off of the concrete. And in this case, the cooling is blown underneath the floor with the blue arrow that point up at the bottom. And the arrows are not pointing up, they're pointing up where there will be perforated tiles. So these are tiles that are on a data center floor. And these perforated tiles allow a certain amount of airflow in CFM, which is cubic feet per minute. And they have different ratings. And you can actually measure the airflow using a flow hood, it's called, and it measures in cubic feet per minute of airflow. And it comes in, it is cooled in the unit over on the far left called a crack unit. This is a computer room air conditioner, computer room air conditioner unit, or it could be a CRAE, which is an H on the end, computer room air handler unit. And what these do is it's like a radiator in your car. The hot air from up above in a false ceiling is sucked over to the crack unit or CRAE unit. It's pulled down through, if it's isolated, it's where you've got some type of plastic or some type of chimney or glass or even sometimes cardboard or whatever, or particle board, small particle board. It will then get pulled down into this crack unit, and it's like a radiator that has saline water. It's water and salt, and it's very cold. So as it comes across this radiator type element, then it cools the air. The heat is transferred into the water that's flowing through this radiator, and then it is then forced out and blown out with a fan underneath to pressurize the underfloor. And then it will go and find the perforated tiles because that's its way out, and it will come up through the floor. And then those blue arrows, there is the cold air pattern. And then these rows are server cabinets, and in these server cabinets are servers actually mounted in the cabinets. And in each server is they air flows from front to back, and these fans will suck in the air, cool off your processors, the main thing that generates a lot of heat. But other elements, hard drives, memory, and other things also can generate heat. It's pulled across those different elements of the server and then blown out the back. So the red arrows is the air, the exhaust air that comes out the back of the server. And then because it's heated, typically it's heated about 30 degrees, 20 to 30 degrees, depending how hot that server is running, how much it's being utilized. All right. And then the air is blown out and the heat rises up. And then there's many times there is openings in the dropped ceiling where you just have those tiles and you have the wires that hold a false ceiling down below the actual floor. And then there's a space between the next floor or the ceiling, if it's just one story, and this dropped ceiling. And this is called the plenum. And within that plenum area, the hot air then escapes up into there and then gets sucked back over into that crack unit to be cooled and then blown underneath as cold air again. Usually it comes out around 67 degrees. It's heated up 30 degrees, so around 100 degrees or 90 some degrees to 100 degrees, and then it's blown out the back. And this, in this case, this is what's called a closed loop. All right, so a closed loop where there's no new air being introduced into the system. It's a closed loop. Hot air is being cooled. Part of that cooling is also some filtering for particulates, which is dust and different things in the air, and that is filtered as well. Also, the humidity is managed by that crack unit to have a specific amount of humidity in the data center, because too little humidity, you can have static electricity, so if it's too dry, and too moist, depending on the temperature of the air, and you can have, and too cold, that combination called the dew point, and you can get condensation. You can actually have water droplets form on sensitive electronic equipment, which is what you don't want, because that can short circuit your equipment, your servers, switches, and other equipment in your data center. Okay, so this is your traditional data center. Well, before this was a data center without rows of servers, so racks weren't put together, they were dispersed around, and then there was a combination, you know, where you just had mainframes, large monolithic devices, and those in a mainframe, you had tiles that were utilized to just randomly separated there. So let me go back to, go down a little bit here. All right. Okay. So other pictures that you can have, okay, is a okay. So there are other cabinets that instead of the air being blown out the back, it's contained within the server cabinet and then funneled up through what's called a chimney. And these chimneys then are then connected to that false ceiling so that it can exhaust the heat directly out through that top area called the plenum area and back to a cray or crack unit to be cooled. And you can see how these work, cold air being pulled in the front through the servers. And then many times it's passive, where there's not fans inside there. Typically there are some, but typically it's just passive with a beveled like aluminum at the bottom that just directs the airflow up above into the plenum area. You can see there's different designs for these, but these then contain that hot air. All right. So so these are things to improve efficiency. So these are more how you have it in the past, or you would have units just out there on their own, okay? And you have perforated tiles. You see right by that man's foot with the blue jacket, right in front of that where airflow is being blown up and then it's being sucked into that, could be mainframe, could be, these are older style data centers where stuff, instead of having rows, it can be more like this where you have different elements and they are separated. And they are separated and dispersed throughout the data center to try and keep the heat that is generated by, heat that's being generated by bigger mainframes, VACs, different types. They're just separated so that they can have cool air to them, but it's a different design. More and more now, data centers look like this. They more have racks tightly butted up against one another in rows. And so in these rows, you have a hot aisle and a cold aisle. And the cold aisle has perforated tiles where airflow blows up and then gets pulled into the front through the actual servers in the room. Now, these other ones, the isolation improves airflow because it doesn't allow hot air from the hot aisle to get back into the cold aisle. So if you have, here's one where this is before they've put the racks in. And you see that all these perforated tiles here are in the cold aisle. And then the fronts of these cabinets will be put in right here next to the perforated tiles. And the airflow will come up through there and get pulled in to the front of all the servers in those racks. And then exhausted out the hot aisle, which is on the back. And so really, two cabinets together in the middle there will, the two exhaust sides will face each other so that heat just goes into a hot aisle and then escapes up above. All right. Now, so there's lots of different designs for data centers, but we've talked about raised floor data centers. There are other data centers here, for example, which are just on concrete. There's no raised floor. This is a newer design of a data center where instead of having a raised floor and having cold air being blown up through the bottom, the data center is isolated with like chimney cabinets or hot aisles. And then the room is pressurized with cold air. So the pressure is throughout the entire room, not just underneath, not the underfloor, but the entire room is then pressurized and there's no raised floor at all. So crack units then, instead of the fan being underneath the floor at the bottom of that cray or crack unit, it's above the floor, it's blown in and pressurizes the entire data center, which includes the cold aisles. And then the hot aisles are isolated so that you you don't have what they call recirculation or airflow. Now here is an older design, and this is not a good design, okay? So you see how all the cabinets are dispersed throughout the data center. And in this case, there is no, it looks like no raised floor, although it may be a raised floor. It could be that the perforated tile is underneath the cabinet and it's blowing air up into the cabinet from underneath. So it's sitting on top of the perforated tiles. And then it's exhausted out into just the data center right there. So, but what happens is if you just had perforated tiles, what can happen is air, if you had perforated tiles in front of that, okay, and you don't have isolation, is that air can blow up through here, come out the back, and as it comes up, it'll circulate around, back around, and get sucked in the front. Now, there's different types of cabinets. Some are glass, so there's no air can go through, and the airflow has to come up from underneath. Most, though, if you look at a server cabinet, okay, okay, you have something like this, where you have the cabinets, you have servers mounted in there. Servers, of course, that go in data centers look nothing like the PCs at your desk. or at home. They are very wide. They're 19 inches wide. They can be 1U, they call it a unit, 1 unit, 2 unit, 4 unit type thing. And these are usually 1 unit is like 1.75 inches. So they go in increments and they're rack mounted. They're bolted into these racks. And they're more like the thinner ones, 1U, are more like what they call pizza boxes. You can do a lot of them, like over in this picture here. I can zoom that up a little bit and bring it back up here. Okay. So you can see a lot over in the far left. All these are 1U servers. And that's a server right there where you've got a couple hard drives at the beginning, and airflow is being pulled in from the front still across those elements. And you can see all those hard drives. That may be a storage area network right there. If it's all storage, you've got PDUs at the bottom typically. These 2 units at the bottom have batteries in them. And this may all be I don't know what this picture is. It could be all storage with management module. I'm not looking at it too closely, but it could be either UPS where it has a battery backup within the rack, or it could be a management module that controls all of this. This could all just be arrays of storage. It could all be hard drives, okay? So let's see, go back down. I easily can zoom it by just grabbing it with my fingers on my other screen there. It's a touch screen. Here's a cabinet, and it's normally just a mesh, just a metal mesh in front that allows airflow to go in. And you can have all sorts of different things in there. You can have switches in there. You see the cabling, the blue cable coming in for switches. You can have UPSs, you can have servers, you can have storage area networks. You can have a network storage. You can have even routers, typically comms rack. There's a server rack, and then there's a comms rack. Okay, and the comms cabinet, I should have said rack, but we'll see what they show us. Okay. This is more a comms rack like this, where you're going to have, this is active, where you actually have devices that are powered up here with the blue and white cabling in this picture. And over to the left, part of that is sometimes that's called a passive rack. If it's all just punch downs or jacks that plug in and allow you to connect, do a cross connect between one device to another using cable. Okay. And so here's more of an open design with racks where they're more freestanding, and you've got servers over here on the right, down at the bottom. And those could be servers, it looks like. Then you have some comms in the middle here with the cabling. Switches, looks like a router and the switch, depending, or a layer 3 switch. And so it could be other comms equipment, could be a WAN router over here on the left, and some other devices. Sometimes those are remote management to view, or remote into these boxes and things like that. So, okay. So all of this equipment goes into your data center, and it must be cooled. The thing about comms racks is when you have a router, okay, when you have a router that does all the connectivity between the servers and out to the different networks. Here you have large enterprise routers from Cisco. This is their 6500 series. And these are ones I've installed and set up quite a bit back when I was a network engineer. But you see that you've got these fans over on the side. So down below, those are fans, but those are power supplies. Those are two redundant large power supplies to power all of these blades, okay? But over on the left, you have fans that blows air through from the side, cools off the components across these circuit boards, these what they call blades, and then exhausts it out the other side. So instead of front to back airflow like a server, you have side to side airflow. All right. And what it's cooling off are these blades that you slide in and snap into a back plane. Here's the back plane on it. These are blades, they slide in and snap in, and they plug into a pin layout in the back. That's a meshed circuit board that has high-speed interconnects between all the different boards or blades that slide in and connect in. And then you populate this as you go. If it's not fully populated, then you have some blades that just have a something on top, like right here, is just a piece of aluminum that blocks that so air doesn't escape out of there. And so yeah, sometimes just leave it open, but you can see how these need to be in a freestanding rack because airflow has got to come in from the side instead of from the front. And if you have it in a cabinet, well, the side of that cabinet is blocking that airflow. So, okay. All right. So again, we have a combination. All right. Now, you see in here, and there are models, 3D models that you can generate of your data center. And you can determine what type of, where the heat, what's happening with the heat and heat generation, okay? And okay, so this is a product that I have used from Future Facilities. It's called a Six Sigma. And what it does is it actually maps through millions of calculations. It maps the air temperature, blue, dark blue being cold, lighter blue, a little bit warmer, light green, green, yellow, orange, and then red being the hottest air. All right. And you can see by these computational fluid dynamic models that airflow, and I'll just expand it a little bit here. This picture, okay. Bring it back up, okay. So airflow coming up here, and then it's being heated, coming up through a cold aisle in the middle of these two rows over on the left. That's your cold aisle. You can see bluer air coming up, and then it goes in to the fronts of those two rows that are facing each other. And then out the back of those racks is the exhaust, the warm air. So as the hot air exhausts out, you see it kind of floating along back to over to the side there on both the right and the left. It's maybe there's a wall there, so it's hitting that wall and kind of just sitting there kind of curling. And these, you can see what happens if you don't have isolation with this cold aisle, then hot air can blow out the back. It can come up over these racks. It's called recirculation, and then it'll get sucked back into the front, okay, of that rack, and then it'll mix with the cold air in the cold aisle. So instead of 67-degree air or 72-degree air being blown into the front of those servers to cool them, then you have warmer air, maybe 75, 78, 80 degrees. And then as it blows across, it's heated from 80 to say 110 or 115 degrees. And that recirculation can cause equipment to overheat and to fail prematurely. Okay. So that's what the isolation does. It blocks hot air from circulating back up and around and getting sucked back in the front of a cold aisle. So these are part of data center design and in an actual data center. Okay. Now, with the cold aisle, let me go back and unzoom that so I can see other pictures. Okay. So these, this is the type of thing that in server rooms, you're trying to help data center or companies with their data centers, make them more efficient. And the better that they can not allow hot and cold air to mix, they can then utilize that cold air coming up through those perforated tiles. And the thing is perforated tiles, depending how much pressure is underneath the floor from your crack units. Also, you know, sometimes you've got impediments because when you have a raised floor, you have a nice clean look because all the power and the data cables go down underneath the floor too. So sometimes you have big bundles of cables that will block or impede the airflow through the underfloor with that raised floor design. And sometimes you think you've got a certain amount of airflow, but you don't necessarily until you actually test it with a little airflow hood. And has anybody ever seen these airflow hoods? They look like this, okay? And you put them up to the vent, and a lot of times they'll use these for air conditioning vents coming in from the ceiling or the floor, and then people will test what type of air conditioning is coming into like an area of your, like an area where, like your workplace, okay? There's your workplace, and they want to see how much airflow, how much cool air is being blown into an office. Okay, well, if you flip it and you put it straight down, you can also test the airflow that's in a data center. All right. So these flow hoods, they call them. Then you flip it there and you stick it on a perforated tile in front of the server cabinet, and you then check, and it gives you the cubic feet per minute of airflow. And you need 300 CFM. Is that it? 300 CFM for every 1 kilowatt of power that's being consumed by your equipment. So there's a relationship. The more power that's being consumed, the more heat is being generated. And so you have to have enough CFM airflow to flow up in front of that cabinet and into those servers. If you don't have enough airflow and it doesn't make it to the top of that cabinet, what happens? You're going to get recirculation. Hot air from the top is going to get sucked around because it's a low pressure area, and hot air is going to be sucked in. So if you're not blowing up enough cold air to be utilized to cool these servers, you've got a hot spot. You got a problem right there in your data center. So this is just a little insight just to view how data centers are designed and how they're cooled, and some of the thoughts in creating these designs. Now you'll notice in this case There's a whole bunch of perforated tiles out here in this raised floor area, okay? But there's no server cabinets around, all right? They're here, but it looks like that's a plexiglass back end, okay? So in this case, cold air is being blown up into the room here from under the floor, and it's doing nothing. It's just blowing up in the room in the data center, and it's not serving any purpose. So part of utilizing effectively your cooling is to remove and cap with just regular tiles, okay? So these data center tiles, you want to cap those off, okay? All right, so these tiles where they don't need to be, you need to, and this little thing right here is a suction cup where you hit it, you push it down on the top of the tile, and it suctions onto it, and you grab that top part of the handle, and you just pull off the tile right here. See, so you just pull it off, and then you can run a new network cable or a power cord or something, whatever you can run underneath the floor, and it's kind of a pain getting underneath there and running a new cable. Sometimes you've got cable contractors that'll run it for you, and that's their job. But you can then, if you leave a tile completely off, one, it's dangerous because it can be from 6 inches to 2 feet or even 3 feet, depending how high the raised floor is, and somebody can fall into that because these are 2 feet by 2 feet, okay, 24 by 24 inches. And then these perforated tiles are in different designs to allow different amounts of airflow to come up from those perforated tiles. You need to put the perforated tiles right in front of the fronts of those servers. If you just stick them out there wherever, okay, then it's not going to be very efficient. All right. And they've got different designs. Some are variable. You can change them. You can see there's different designs. 70% rate, 22%, 25% is standard. 30, 36, 45. You can see the different holes, the sizes of the holes, the perforations. It allows more air out. Okay. So these come in different designs to allow different airflow to come up through the floor and to be utilized for cooling in your data center. This is below the floor. You can see the stuff that's running below the floor. You can see the frame of the floor here. Okay, the frame has to be obviously strong enough to hold all the servers, the server cabinets and all the equipment and the comm racks and everything above it. So it's got to be strong enough to manage that weight, and that is a lot of weight. And okay, so this gives you a little look at little data center design. Here you see that they have cold aisle is not isolated, but the hot aisle is isolated. Cold air is coming up through these perforated tiles. It gets pulled into these racks, these white racks, heated up as it goes across those hot elements in the server, and exhausted out the back into this hot aisle area. Okay, now typically another rack, I think that's the case here, is on the back side of it, and those are, facing the other way, so the hot air comes in as well from the other side, and then this is exhausted up to the ceiling so that you are isolating the hot air and the cold air. Okay, so this is a good picture of it. Okay, all right, so these are just a little more idea of what goes in. You put all of your cabling and power, here's your fiber optic in the orange, and your copper and other runs. They have underfloor trays that holds this, and you try and keep it separated. Now, you put this through your hot aisle so that it's not running in your cold aisle and blocking airflow getting into your cold aisle. All right, if that makes sense.
Yeah, I just want to jump in here real quick. You definitely need to have cooling in your data center because each of the servers consume anywhere from 500 to 1,000 watts, and you've got hundreds of servers in your data center usually. And so you're talking a lot of heat generated. Um, in our data center in Louisiana, we had a very similar setup to what he's talking about here with the raised floor. And one time the cooling went out on it. And we had a data center hit about 100 degrees within about 15 minutes. And so, yeah, it was not a good plan, but we had to open up all the doors to the data center and put, it's box fans basically to try to blow cool air in there. Got it down to around 80 degrees until the AC guy could come and fix it for us.
Yeah. Yeah, that's exactly right. So because so much equipment is in one condensed area and so much power is being consumed and that drives, that's generating heat through these, this constant cooling. And so redundancy, we talk about redundancy with network, so your network doesn't go down. We've talked, redundancy with like redundant power supplies. So if one of your power supplies fails, your server's still running. But there's also redundancy in cooling systems too. And you can have actually a primary and a secondary cooling piping that comes into these crack or cray units from different cooling systems. So if one fails, one's still going, and so forth. So all this is, these are elements of cooling and power. Okay. Now I want to plug in, let's see, this is still plugged in, right? So I want to talk about some terms. Okay. Okay. So, hold on a minute. Okay, so I gotta verify these numbers because I'm forgetting them. All right. All right, so let me minimize this here. I'll create a new one here. Okay, so there is a term called, PUE, okay? Power usage efficiency, okay? No, it's not power usage efficiency, it's power usage effectiveness. Oh, that's interesting. Huh? Okay. Power usage effectiveness. Okay, this is a term for data centers, all right, where they determine how efficient is our data center, okay? And this PUE is really a ratio, okay? It's a ratio of the amount of power coming into the data center with the amount of power actually ultimately going to your IT equipment, okay? So power, electrical power, okay, yes. Power goes to IT equipment, right, to power it. But it goes to other things too. It goes to lights. It goes to cooling, which is a huge amount of power to cool with a closed loop. We talked about closed loop. It's very inefficient because you are trying to cool hot air. Okay? So in a closed loop, it's very inefficient because you take hot air, you cool it, you pump it back underneath the raised floor. It comes back up, between 67 to 72 degrees Fahrenheit. It comes in and gets heated again, and it goes up to that plenum that between the false ceiling and the next floor, and gets sucked back down, and it does it all over again. Okay, so you're always cooling hot air, so it's very inefficient. That's a closed loop. Okay, it's very inefficient. Okay, and it consumes a lot of power to cool that hot air all the time. So you've got other elements that are in there. You've got sensors. You've got a UPS, which is a battery backup in case there's a failure. Okay, that you've got to store power in all the time. And so this is basically stored power. But basically, you are charging those batteries all the time. And then you have your power, okay, distribution. And power distribution is coming in from the high tension power lines and breaking down those high voltages into it's coming from, power station across high voltage lines where you've got 400,000 or around there, 300 to 400,000 volts. And then it's broken down into a grid substation. Okay, then you've got 132,000 volts. Okay, it keeps being broken down into these different other substations till it comes into schools and houses. If it comes into a school, it comes in at 400 volts and then broken down again within the school with some power distribution equipment to your 110 and 208. 240 volts comes into your house, and that heats up your 208 and 110 circuits in your, but also heavy industry. It comes in from high end and then gets broken down in your data center. All right. So these pieces of equipment, they look like this. Okay. High power lines come into your data center, and then this is broken down into voltages that your IT equipment can utilize. All right. Well, part of that power distribution is that when it finally gets to your server, you've lost some power in the breakdown process. So when it goes into these power distribution, it comes in, it's broken down into voltages that can be utilized in your data center, okay, and then run across into your data center across different different strips or power blocks, okay, to plug into. You've lost some of that power to heat. So you lose some power to heat, okay, as it comes into these power units and is broken down. And even when it goes into your server, when it plugs into your server here, right here, and it plugs into your server, these power supplies are not 100% efficient. they're 95% or 98% efficient. So your power supplies also heat up and lose some power to heat as well when it goes into your server, and it's used for memory. The motherboard, the processor is probably one of the biggest consumers of power in your data in your server. Well, as those heat up, also the hotter they run, the more power they consume too. It's called leakage in the silicon. So everything has this power loss in all of these steps. So power distribution from the high voltage equipment, okay, the initial equipment, okay, to not 100% efficient power supplies, and then depending on the heat, how hot devices run, they can be consuming more power based on how hot they run. So there's also, I forgot in between here, there's initial power equipment. Then it usually comes into a rack. At the rack level, there is a PDU, power distribution unit. Okay, and that of course loses some power to heat. Then you got the power supplies in your servers, okay? Servers. Okay, and then you go, and then how hot these devices run. So all these things basically, basically you lose power all the way along the way. And so it's one, how efficient are your devices running? And then how efficient overall is your data center as a whole with power to go to the fans or sensors or you've got other elements of backup. You've got PDUs. You got UPS. What else you got? Anything else, Peter? I'm not thinking of.
You're covering it pretty good there. I'm chatting with some of the guys about PUE calculations.
Okay,
They
so
had,
this PUE, and a good place even you can just go to Wikipedia and do PUE. And this standard, okay, so if you search for this, power usage effectiveness right here. If you go to power usage effectiveness, this is what it is. It's total facility energy divided by IT equipment energy. Okay, and plus non-IT facility equipment energy over IT equipment energy. So what this equates to is it becomes a number called, the closer to 1 you get, the more efficient your data center is, okay? So if I look at just this right here, okay? All right, so 1.0 is perfect power distribution, no power loss, okay? That is theoretical. That's never going to happen. But you can get very close to 1.0. Okay, you can get a 1.1 or 1.2. High-end data centers, public cloud providers, Azure, Google, Facebook, Amazon Web Services, they can get very close to 1. And that just means that almost all power coming in, they have very highly efficient power distribution equipment. And so almost all power gets to their server and IT equipment, okay? And even just 5 years ago, 1.5 was good. 10 years ago. 1.5 was very good, and 2 was even still pretty good. But what 2 means is now that's poor because only 50% of all the power that's getting from the power lines to your IT equipment. The other half is going to other things. Cooling, probably number one. Power distribution losses through heat generation, lighting, other fans, other security systems, and other things. So all those things. So only half of the power. So you're paying for twice as much power as you would normally need if you had a more efficient data center. And what that means is you're spending a lot of extra money that you don't need to. And that's a competitive advantage because if you are saving, and these costs of power, power is the largest cost of a data center, all right? It's more, it winds up being because you pay your power bill year after year after year. You know, to build the data center was only so much cost. The equipment, even just, even changing your equipment out every 4 years, power still is the biggest cost. Besides servers, besides salaries, everything, looking at power is the highest cost of a data center. So that's why we want to try and improve the efficiency of the data center. This chicken coop, I throw this in here because this is a good example of trying to be more efficient. So Yahoo, okay, has what's called a chicken coop design, not these chicken coops. This chicken coop right here. Okay. Here's the design of their data center. And instead of having what I had termed closed loop, okay, what I had termed closed loop, another way to look at this is open loop cooling, okay? So there's closed loop, which we've talked about thus far. Open loop this is a good example of open loop, okay? So the air behind this this is like 12 feet high, I think, or 10 feet high. And I did a design in this data center up in Buffalo for Yahoo. I was in this data center, or several data centers here. And they have huge fans behind this wall here. This is a vent. And it has some filtering. Okay, it has a pad that does some filtering for dirt and other things. And then it comes through with these huge fans. So they suck in outside air. Then they pressurize the room with this outside air that's already cool. Now it has wide fluctuations because different times of the year is different temperatures, but it gets pulled in. It gets utilized to cool the servers, and then the servers, the heat then goes out the top. Okay, it looks like some massive chicken coop. All right, but it goes out, it comes in, cools the equipment, then the hot air rises and exhausts out the top of the chicken coop. All right, so it's a open loop cooling. And even though these are huge fans, they take just a fraction of the power to spin these fans to pull in cold air from the outside than it does to cool hot air using some type of closed loop system. Okay, because power is being consumed to cool the liquid in a constant circuit. This is much more efficient, just pulling outside air. And yes, there's wide fluctuations in temperature, wide fluctuations in humidity. So they have humidity sensors to sense what the humidity is, and they have sensors on the temperatures it comes in. And if it's too cold, then you'll just see this return air as required. They'll mix some hot air right here with the incoming cold air, because Buffalo can get very cold. And then they will mix it with hot air that was being exhausted. So they will mix it and get the right mix. So they're constantly monitoring this. But that has caused them to have a PUE of 1.2, and they want to get down to 1.1. So that is just one example of ways to improve or reduce power consumption. One way is to have open loop cooling.
Another example of that. Yeah, another example of that, Mark. I read an article recently where Microsoft is actually making a submerged data center in the water and using the water's natural coldness to cool off their servers. I thought that was interesting.
Yes, exactly. This is it right here.
Oh, you got it.
Yeah. So let me pull it up here. Okay. This is Project Natick, and they've done 2 submersibles with this. And there's a video of this. And what they did is they created this. It might be farther down on this page, but it's starting to slow down. Come on.
The overarching goal.
So basically, they put this thing out to sea, and you can watch this if you want. But basically, that's the data center right there. They mounted it to the base. They put a bunch of servers in racks in the thing. They submerged it in the ocean. They used the cold water, seawater, to cool these servers. All right, while it was underneath, but obviously it was a self-contained data center. You're not going to be able to go in there and reboot a server. Okay, everything has to be remote, obviously, for this thing. And of course, they have cables that include data cables and power cables down to it. And then they have been doing this testing here to see the feasibility of doing an actual data center underwater, and use the obviously the seawater that's already cold, and use that for cooling and have it completely self-contained. The idea here was that you could drop this data center, a portable data center, into the water, because what is it, 90% of the world's population is by the ocean. So you could drop a data center right by a population center and have immediate access to compute power. That you could drop these things. You also have container data centers. Okay, so you have container data centers, and these babies could be dropped on land. Okay, and they're like this. Okay, and you've got racks inside a container. This is a shipping container, basically. Okay, so shipping containers, you drop these things, you ship them in, you can bring them in like that, okay, from boat, or you could bring them in on a semi trailer and drop it in, okay. This is this is Microsoft's data center in Chicago. This is one version of a Microsoft data center. It was a container data center. And you have on the top, I believe, is the cooling. Many of these containers are self-contained. Others, one container is the servers and the other container is all the cooling infrastructure to cool and push air down into the other container. So sometimes that's the case. And they stack them, it's like a warehouse, and they stack them in and then provided power to them. So you've got container data centers as well. And so yeah. Okay, I want to show you a quick video. And I will stop sharing for a minute here. And let me share again with actual volume. And I'll show you this. Share screen with sound. Okay. Okay. So let's see if this comes through. And look at the different elements in this. This is only going to be approximately 2 minutes here, okay? Let me unmute it. You guys hear the volume?
Yes.
Okay. So you see that it's a quick little video, shows a lot of different data centers in different locations of the world for Microsoft with their Azure data center infrastructure. And they have a lot of, what were things that you saw in this that you thought were interesting? What about this right here? So they're 100% carbon neutral, meaning they're trying to power their data centers with hydroelectric, solar, wind, ocean current, things like that. They believe they've accomplished that. So they're not adding to our carbon footprint with, say, coal-fired power plant type deal where carbon is emitted, right? Okay. Trying to be not polluting. There's a term called a green data center, and most data centers cannot have all power coming from carbon neutral, but a data center can take the amount of power of a small city, Okay. So there's not really anything green about them, but they like to say that term. It's a buzzword. But you also have monitoring. You have to monitor all these systems. It's important when you have a huge data center and other people are using this and leasing virtual services from you, like Azure or Amazon Web Services or Oracle Cloud Infrastructure, OCI, that this stuff stays up and running. These are good jobs in data centers, network engineers, monitoring, support. There's lots of different jobs that are related to these in high tech. What are these? You want to take a guess?
Looks like server racks, right?
This is outside. This is external to data center. So this is a multi-level data center, but this is from the outside, I believe. I believe these are the generators. But we know that these are generators right here. Okay, those are large, using Caterpillar and other manufacturers create large diesel generators that you see there's two here because everything's redundant. Generators are redundant. Power from different feeds are redundant. Cooling is redundant. Internet connections are redundant. Everything is redundant because there cannot be any single point of failure. Or if you do all this redundancy and then you have one internet feed and the internet goes down, people don't have access to your data center. So everything has to be redundant. So that's why the cost goes up with there's different tiers, tier 1 through 4 with data centers. And that's, determines the redundancy. And of course, tier 4 is high, and there may be a tier 5 now, but it's very expensive. But the cost is shared by everyone who leases equipment in this data center. Unless it's not private, but yeah. So those are backup generators. Okay, these, what's that?
Batteries.
Yep, those are like deep cell marine batteries or something like that. But they're batteries basically to support the data center if the power goes out. But all they do is keep power flowing to the data center until the generators kick on. Many times you can have rows and rows of these batteries, and it only provides you a half hour to an hour of uptime. The generator should kick on in 10 seconds. Okay, should normalize, and within a couple minutes should be having power that is consistent power from the generator. So that's what these batteries are, is to keep power going to the equipment, IT equipment, until the generator gets up and as a steady state RPMs and is running and is warmed up and ready to go. Okay. And these, what are those? Those are power distribution boxes up above your server racks where power comes down from those. And those are dynamic power circuits that can be changed, modified. Okay. Here's some power distribution equipment over on the right, servers and so forth, I believe, over on the left. Okay. Here's your actual server row. It's pressurized in there, so there's no raised floor, you see, and all the cabling goes up to the top and goes across the fiber optic and copper cable management, okay, on the top instead of underneath with a raised floor. Here's just a cable into a passive rack there for connectivity, right? there's a thing called lights out data center. So the lights, literally, there's no lights turned on because nobody's in the data center. And it's totally remote. That would be what they call a lights out data center. And or they have them on just a sensor. When you walk in, they all turn on. So you're saving power with motion sensors. Okay. All right. Now, where are the locations of these data centers? These data centers need to be typically on the edge of cities, so they can have cheap property taxes. They usually, the one in Quincy, Washington is right by the Columbia River, and they've negotiated cheap hydroelectric power rates for their data center. And Quincy is just a little farming town. If you look it up, I can point you to it, but I think it's 2:20, so we're out of time, but we'll show you that another day. But yeah, Quincy is where the closest Microsoft Azure data center is located to us. And okay, so hopefully that gives you a little more understanding of data centers and what they can do, how they're made up, the elements that you're thinking about in cooling, in power costs, in ways to make data centers more efficient with different types of cooling, open and closed loop, and different terms like PUE, power usage effectiveness, and so forth. Okay. Any questions to wrap it up here?
I had a very quick question for you, Mark. The two specific, one was on the phrase plenum. As far as I understood, plenum would normally mean that buffer space, or it could have materials in it. But in this case, we're talking about a specific type of airspace. Is that correct with plenum? And then the second term is that you mentioned that they had an optimal heat range that you did want your data centers to be. And I don't know if you mentioned the low end of that separate from just accounting for humidity.
Yeah. Well, what we found is an optimal range. Data centers usually try and stay at around 67 degrees Fahrenheit. The air coming in is that temperature, and to try and keep the colder the equipment, it can't go down to freezing. Okay, but there's environmental conditions that the server has to run in, and it shows it on the user manual. When you buy it and unbox the server, it says this has got to be under 10,000 feet. It's got to be between this temperature and this temperature. It can't be too cold and it can't be too hot, but it's a very wide range. So because there's a wide range, it allows flexibility in what you cool your data center. Some, they call it high temp data centers. Okay. And so they've said, well, why do we spend so much money cooling our air to 67 degrees? Why don't we just cool it to 80? Well, that introduces other elements, because the second that you got a failure in your cooling, in a matter of 5 or 10 minutes, you're over 100 degrees. So you got to be very careful. And so yeah, you got to have enough airflow. The hotter it is, the fans detect that on the server. There's a sensor on the motherboard. And so it'll kick in the fans and it'll increase the RPMs higher to blow more air across your components to cool your server and your processor. When the air is hotter, it needs more airflow. So that's something else to think about. The hotter the air, the more airflow to cool it and to extract that heat from the server and the components inside the server. The plenum, yes, is that open area of air, that space in between the drop ceiling or the false ceiling and the next floor or the actual physical ceiling of the data center.
I want to sneak a last quick question, and I hate to keep you guys, but it caught my attention talking about the PUE. Having come up through the ranks, I noticed that a lot of the original computer systems obviously had very heavy power supplies, used a lot of wattage, a lot of heat, and as the components obviously went more monolithic and got smaller and fanned out with lower and lower voltages, including the processors, that was an automatic win for having a lower energy board. But obviously, whenever the data center should be able to account for the loss when you're transforming AC power, back into DC for each of the individual units. Those PDUs that you showed, Mark, is there a push to kind of get rid of the AC conversion factor at each unit, and the PDUs just distributing the DC voltage to those new blade systems, or am I don't know if it's still.
Yeah, 48 volt DC direct current directly to those, and DC is more efficient, but you have every piece of equipment then has to be direct current capable, and
Right.
it's sometimes a special thing to get power supplies that are DC based and the equipment. So it's but there are those people that they're pushing towards direct current, and but by and large, the majority of energy and is still AC in data centers.
Okay, because I'm not an engineer in that area, but obviously the step down transformers, there is a calculated loss each
Yeah.
time you take that larger voltage and kick it down.
That's right. That's exactly
Down.
right. That's what you're losing power, and your efficiency of your data center is going down. That's right.
Okay. Okay. I appreciate you addressing those. Thank you.
Yeah. All right, everyone. We'll see you Thursday at 1 o'clock.
Bye.